we present PINA, a method for learning a personalized implicit neural avatar from a single RGB-D video sequence. Our input is a single RGB-D sequence. From this sequence, we learn continuous implicit shape and skinning fields to create a detailed and personalized virtual copy for non-expert users. The final avatar can be animated with realistic clothing deformations. Learning an avatar in this setting is challenging, since there are only a few depth frames to learn from, and since the depth observations are noisy and incomplete. To solve this, we propose a method to fuse partial depth maps from the whole sequence into a single, consistent representation. Specifically, we define an implicit signed distance function and a deformation field in canonical space to represent the shape and non-rigid deformation of the avatar. This representation is learned entirely from the partial point clouds. We first sample 3D points in deformed space. Both points on and off the body's surface are sampled. Given poses derived from RGB-D sequences, the corresponding canonical points can be calculated via an iterative correspondence search. We condition the SDF network on the pose, so it can learn to handle pose-dependent deformations. We estimate the SDF value and the normal of these points in canonical space, and then map them into deformed space via linear blend skinning. We compare these predictions with the input observations, and jointly optimize the pose, shape, and skinning parameters to learn PINA. With this learned representation, we can generate animations of the avatar in unseen poses. Here, we show some of our results. Note that all avatars have been learned from real-world RGB-D data. Because our method does not rely on data-driven priors, it can learn arbitrary garment styles. Here we demonstrate the ability of our method to reconstruct even uncommon clothing. Note that even when reposed to a very different sequence, the avatar displays realistic clothing deformation. This generalization to new poses is independent of the subject or garment. We also demonstrate that our algorithm can generalize to different human shapes. Finally, our model can capture fine details, even those that are difficult to capture for most depth sensors, such as the hair of this female subject. While our model produces plausible animations of the avatar, we leave the full treatment of hair animation for future work. Finally, we conduct ablation studies and comparisons to state-of-the-art methods. First, we ablate the benefit of our global optimization formulation. Here we show that optimizing the shape and pose jointly leads to more faithful geometry. Please pay attention to the head and the trouser leg. Next, we show the effects of our deformation model. Without learned skinning weights, the deformed regions can be noisy and display visible artifacts. Without pose features, the shape network cannot represent the dynamically changing surface details of the blazer. Finally, we compare our method to existing state-of-the-art methods in the envisioned application scenario of avatar animation. Thank you for watching.